everyone, and welcome to ML Done. This is Mehran. So today we're going to continue with our lectures on concept learning and general to specific ordering. But first, let's do a quick recap on what we talked about the last time. We defined this relationship called more general than or equal to between two hypotheses. And we said that hypothesis J is more general than hypothesis K if and only if for any instance in our instance space, if all of them that can satisfy hypothesis K can also satisfy hypothesis J. So this is the only circumstances under which we can say that hypothesis J is more general than or equal to hypothesis K. Basically anything that can satisfy H of K should be also able to satisfy hypothesis J that we've denoted with H of J. Today we're going to talk about our first algorithm called find S, which utilizes this relationship to have a smarter search in the hypothesis space H. So there are different ways that this machine learning algorithm can search through the hypothesis space, yeah? One particular way is to start with the most ridiculously specific hypothesis possible and then gradually generalize it, make it bigger and bigger, more generalized. But the way we do that is going to be through this algorithm called find S algorithm. And as the name implies, it looks to find the most maximally specific hypothesis. So let's say that we initialize H, which is our hypothesis, as the most specific hypothesis in our hypothesis space, yeah? And then you have to go through all the positive, and I'm insisting here, positive training examples in our training set, yeah? One by one. Then you have to figure out whether this particular X, say the first one, satisfies my current H or not. Yeah. So for example, if you consider H something like this, so say H has A1, A2, and A3. So these are the constraints for the first attribute, second attribute, and the third attribute. Yeah. And say your first example, X of 1, has, say, value 1, value 2, and value 3. Yeah, so some values, whatever they are. The way this find S algorithm works is that it would grab the first positive example in the training set, let's call it X of 1. Yeah, and then for each attribute constraint A sub I in H, so meaning that for each one of them, A1, A2, and A3, what we do is we check whether the corresponding value in X of 1 satisfies that constraint. For example, let's start with A sub 1. Does V sub 1 satisfy X1 or not? Now, what we do here, now if V sub 1 satisfies that constraint, then we basically do nothing with A sub 1. Basically, we do not touch this. We say, okay, you're good. We're not going to change you. We don't need to generalize you. Okay? Stay as specific as you are. Then we go to the next one, the next constraint, A sub 2. And then we ask ourselves, does V sub 2 satisfy A sub 2? Now, let's say in this case it doesn't. Then we have to change A sub 2, right? Change to what? We have to ask ourselves, why doesn't V sub 2 satisfy A sub 2? It's because A sub 2 is too specific. So we need to basically generalize A sub 2, but just enough so that it would accept V sub 2, right? So you don't have to go wild. You don't have to make it super generalized. Yeah, so just generalize it enough so that V sub 2 would be accepted. And that is why I have this bit over here. See? If not satisfied, then replace a sub I in your hypothesis by the next immediate, more general constraint that can be satisfied by X. Yeah? And then you will continue until you finish all the constraints, and you will generalize each one of them that you have to, and then you will go to the next training example, and next, and next. All the positive training example, remember, this is a key thing here. We go through positive training examples. Yes? And then when we reach to the end of the training examples, we output the hypothesis H that we have learned by the time we have reached the end of our training set. Now, the best way to understand this is through an example, yes? So, based on the algorithm and this table over here, we have the attributes sky temperature, humidity, wind, water, forecast. And the concept that we want to learn is called play, whether Joe's going to play golf or not on that particular day. Now, based on the algorithm, we have to start from somewhere, right? We have to start from hypothesis. So we would start from the first hypothesis that is the most specific one, right? And what would be the most specific hypothesis? You can pause the video and think about it. Think about the constraints that we've talked about, right? So basically, you can say nothing, 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 again, nothing, nothing, and nothing. So this is basically a null hypothesis. It says nothing goes. I will not classify anything as positive. It means doesn't matter what type of a day you put in front of me, with what type of values for each one of these attributes, I will not classify them as positive. They will not satisfy me. So this is like basically a point in the hypothesis space, right? Now, based on the example, based on the algorithm, we go through the first training example, which is positive. Then we ask ourselves, we have to go through each one of the constraints, 1, 2, 3, 4, 5, 6 constraints individually, and ask ourselves, does the corresponding value in our example, our positive example, satisfy that constraint or not? As we can see, obviously none of the null constraints can be satisfied by the values of the attributes for our first training example, yes? So if they're not satisfied, what we have to do is we have to generalize each one of these constraints, but not just any generalization, yeah? We have to generalize them to the next immediate level, right? So just generalize them enough that they could be satisfied with this example. So you can think about it, but I'm gonna go ahead and write the answer. Just pause the video and think about it. So what is the next type of constraint that you could put here that can be more general than h of 1's constraints, but at the same time it would accept the positive example 1 as positive? The next immediate answer would be the exact values that we have in our example. That's all you have to do. Strong, warm. You see, I'm just copying the values for x of 1. Yeah? Cool. Then based on the algorithm, I have to go to the next training example, or positive training example, which is example number 2. Now, what should we do here? Again, look at the constraints. Now our constraints are specific values in h of 2. Yeah? So as you can see, I used this idea of more generalized than or equal to search through our hypothesis space H, and that is how it helped me. I jumped from h of 1 to h of 2. I'm not just blindly choosing values here. Okay? Now, look at example number 2. We got sunny, warm, high, strong, warm, same. Now, look at our hypothesis h of 2. First constraint, sunny. Is it satisfied? Yes, we have sunny. So Yeah, this constraint is fine. Check. Next one, warm. Is that satisfied? Yes, it is satisfied because we have warm here as well. Next one, normal. Is that satisfied? Oh no, that is not satisfied. So what do we have to do? We have to change this to the immediate, more general version. So remember, we have had 3 constraints, yeah? Null, exact value, and the question mark. So the immediate next general constraint that we have is a question mark. So basically, we would change this to a question mark. What about the next? Is a strong satisfied? Yes, it is. Warm? Yes, it is. Same? Yes, it is. So what I have to do is basically, I'm not going to change any of these constraints. So still sunny is sunny. Still warm is warm. Normal change to the question mark, meaning anything goes. We've got strong, got warm, we've got same. And this is the next hypothesis that we learned. Hypothesis 3. Now, as you can notice, because of this question mark, now H3 hypothesis can be satisfied with both example number 1 and example number 2, both of which are positive examples. Now, find S algorithm doesn't even bother with example number 3 because it is a negative example. So we don't even have to bother with this, okay? We have to jump over it. But remember, automatically, if you look at the values, it is already rejecting example number 3, right? Because just starting with the first one, it has rainy for sky, but we only accept sunny for sky. So right there, example number 3 is rejected and cannot satisfy H of 3. So basically, H of 3 would classify example number 3 as a negative example. So it's already right. Later on, I will explain to you why the find S algorithm doesn't bother even noticing the negative examples. It has a very interesting reason. Now, let's go to the next positive example, which is X of 4. Again, we'll go through the same reasoning. First one is sunny, yeah? And it is satisfied. We have sunny. Next one is warm. It is satisfied. Cool. Next one is we don't care. Already satisfied. Next one is strong. Satisfied. Next one is cool. Oh, not satisfied. We have warm here. So what do we have to do? We have to change it. What is the next immediate, more general constraint? It's a question mark. And then what about the last bit? We've got change here, but we have same here. So again, doesn't satisfy that. So we have to again change the same constraint into a question mark constraint. So, and we would just copy and paste the other constraint. We're not going to change any of them. Warm and sunny. Now you can pause the video and just look at hypothesis number 4. We have reached the end of our training examples, and H of 4 is what we've converged to. So we searched through our hypothesis space, capital H, the way we show that, and we jumped from H1 to H2 to H of 3 to H of 4, and the way we did it was through utilizing this relationship called more general than or equal to. Now, we need to focus a little bit more on this algorithm, so I'm going to explain a couple of bits. Now, the big question, why doesn't find S bother with the negative examples? To see why, remember that we have started with H as the most specific hypothesis, right? But remember that at any stage, at any stage during our exploration of our training examples. What is H? It is the most specific hypothesis, that's called hypothesis, consistent with the observed positive training examples. Remember that. The key thing to remember here is this bit. It is the most specific hypothesis at any stage that is consistent with the observed positive training examples. Perfect. Now remember, why are we searching? Because we want to find C. We want to find this hypothesis called the true hypothesis. Why? Because that's the hypothesis that fits our training examples perfectly. But then again, remember that this C is also consistent with positive observed examples. So no problem with that, because we're sure that C will classify everything perfectly. And we know that at every step during our exploration, every H that we converge to, every H that we learn, is the most specific one, right? And there is a C somewhere in that hypothesis space that we're trying to find. So based on all of this, we can say that because the target concept C is also assumed to be in our hypothesis space, and it is also consistent with all the positive training examples, then this true hidden hypothesis C, behold, must be more general than or equal to our hypothesis H, right? But remember that the target concept C, because it is perfect, because it fits our training examples perfectly, remember that it is consistent with our negative examples as well. So what it doesn't do, it never covers the negative examples. Now I'm asking you, because now we understand what this definition means, then we can say that since target concept C will never ever cover a negative example, thus neither will the hypothesis H, right? Because when C is more general, when C is stronger, more encompassing than our hypothesis H at any stage of our exploration, and if the negative examples cannot satisfy that hypothesis C, and C is more general than or equal to hypothesis H, then how could those examples satisfy our hypothesis H? And that is why, as we are searching through our training examples, we do not bother with the negative examples, because we already know that H will not be satisfied by them, because at every step, H is the most specific hypothesis consistent with the observed positive examples up to that point. Right, some final remarks. Number one, find this algorithm is not perfect. In the next video we will cover some of the issues with this algorithm, but not for now. And then remember that we are assuming that our training examples are error-free. Just think about that. That if there is a negative example in our training set and it has been labeled as negative, right? And then we would change our hypothesis based on that example. We're basically trying to make our hypothesis satisfiable by a truly negative example, right? Because it is actually negative. But because there is a error in the label in our training set, we are basically disrupting our search in our hypothesis space, and we will converge to the wrong hypothesis. And remember that this basically, I love this bit because this is one of the summaries that would put everything together. At any step in our search, the obtained hypothesis H, what is it? It is the most specific hypothesis in our hypothesis space that is consistent with the observed positive training examples up to that point in our search. And last, the way we generalized the constraints in our hypothesis was we first initiated them with the null hypothesis, and then we made them more generalized when we had to a specific value. And then, if that failed, we jumped into question mark. So as you can see, the jump from here to here, well, it seems like a very small generalization, yeah? However, the jump from here to here looks like a wild generalization, yeah? And this is not necessarily a good idea, but remember that the find us algorithm doesn't bother with the way we are generalizing. Yeah, it just says if the constraint failed to cover the example, just make them more general, just enough to cover that example. Yeah, but the way we have worked on so far is that we have just defined 3 constraints, and the main point is just to convey the main teaching of this algorithm, and that's it. Great, lovely. I hope that you've enjoyed this video. So in the next video, we're going to talk about the common issues with the find us algorithm. And I hope that this has been informative for you. If you liked the video, please don't forget to like it and also subscribe to our channel because we're going to be uploading more and more videos about different exciting topics of machine learning. Moreover, if you want to dig into more details, there's a link to the blog post that goes into more details about this particular video. And also there's a link to our website, mldon.com, where we have also different variety of courses that you can enjoy. And you can also follow us on Twitter and Facebook. And that's it. So until our next video, take care of yourselves on behalf of MLDon, and goodbye.